Hi everyone, I'm deciding to make a video here when we study linear independence because this is a topic I'd like to get kind of all the way through the presentation of the ideas before we dive into problems or questions together. So I hope this helps you get a sense of what linear independence means, as well as understanding some of the formal definitions. So I know that as we've been doing the section so far in the chapter, we've been developing a good intuitive sense of what it means to be linearly independent or linearly dependent. But I want us to focus a lot of our attention in this lesson on the formal definition and how we can use that to show whether vectors are independent or dependent. Okay, so I'm going to start with that formal definition just written out explicitly. Okay, I think it's important that we see that at least once. All right, so an indexed set of vectors v1 to vp in Rn. So let's take stock of what that means so far. So index just means that like we can list them like the first vector, second vector, third vector. There are p of them, which means that, that's the number of vectors, and then there are n components in each vector. So if we were to put those vectors in a matrix, it would be an n by p matrix. Okay, so this set is said to be linearly independent. This set is said to be linearly independent. That's the thing we're defining. If the vector equation that looks like this, x1 v1 plus x2 v2 all the way out to xp vp equals 0. So we're talking about some feature of this equation where all of the x's are scalars and all of the v's are vectors. If this equation has only the trivial solution. Okay, so this is related back to what we studied in 1.5 with homogeneous systems, because essentially what we're looking for here is no free variables, right? We have an n by p matrix with no free variables, meaning that there has to be a pivot column in every column of the non-augmented matrix. Okay, we'll state some of that formally later on, but that's the key to having a linearly independent set, that the only scalars that would work in front of v1, v2, etc. are zeros. Okay. All right, so the set, let's kind of say the opposite of that, right? So the set v1 to vp is said to be linearly dependent. That's the opposite of linearly independent, right? So the set is said to be linearly dependent if there exist scalars C1 to CP, not all zero, because if they were just all zero, then we'd have a linearly independent set, right? So they have to be scalars C1 to CP, not all zero, such that C1 V1 plus C2 V2 all the way out to CP VP equals the zero vector. Okay, in other words, there is a non-trivial solution to this vector equation. Okay, this thing that I just wrote, when not all of the scalars are zero, this is called a linear dependence relation. It's called the linear dependence relation. So a non-trivial solution to the vector equation gives us a linear dependence relation. Think about how that's related to the material that we covered in 1.5. This means that if we were trying to solve ax equals 0, if we have only the trivial solution to this, then we have linearly independent. If we have at least one non-trivial solution, then we have linearly dependent. Okay, and What that means is that there are columns, when something is linearly dependent, when a set is linearly dependent, that means that there are columns that can be written as linear combinations of the other columns. That's actually a formal theorem that we'll talk about in a little bit. Okay, so let's take a look at an example. We're going to start with small sets because those are easy to deal with, small sets that are in R3. So for our first example, we're going to take three vectors in R3. Okay, so we're going to say V1 equals the vector 1, 2, 3. V2 equals the vector 4, 5, 6. And V3 equals the vector 2, 1, 0. And the question is this set linearly independent? Okay, is this set linearly independent? Well, to answer that question, we have to solve x1 v1 plus x2 v2 plus x3 v3 equals 0. In other words, we have to determine, are there scalars that we can put in front of each of these vectors to reach the 0 vector? Or another way of phrasing that is any of the vectors in this set a linear combination of the other vectors? In other words, can I make v1 out of the other two vectors? Can I make v2 out of the other two vectors? Can I make v3 out of the other two vectors? If any one of those questions is yes, then the set is linearly dependent, and there is a linear dependence relation, meaning there are scalars that we can put in front of the three vectors to arrive at the 0 vector. Okay, well, just like everything seemingly so far in this course, we solve this equation by rerefing, and it's rerefing a matrix that has the three vectors as columns and the 0 vector as the final column. Okay, so we're going to do that. We'll see what comes out of this, and that will answer our question. So let's reref the matrix that we have here. Okay, so we have a 3 by 4, 1, 4, 2, 0, 2, 5, 1, 0, 3, 6, 0, 0, and we get this. I'm going to copy and paste that over to our notes so we can study it. The first thing to observe here is that we definitely do not have a pivot in every column. Right? We definitely do not have a pivot in every column. We do have a free variable. X3 is a free variable. Therefore, right away, our answer to the question of is it linearly independent is no. This is a linearly dependent set. Okay, just by the existence of a free variable. So from that now, let's write a linear dependence relation. Let's actually state how the vectors relate to each other. So we know that x1 equals 2x3, x2 equals negative x3, and x3 equals x3. Or written in parametric vector form, that's x3 times 2, negative 1, 1. So this means that 2, negative 1, 1, or any scalar multiple of 2, negative 1, 1, is a solution to our original vector equation. So I could write 2v1 minus v2 plus v3 equals 0. This is one of the infinitely many linear dependence relations, right? Linear dependence relation. So what this shows is that v3 can be written as a linear combination of the other two, because we could solve for v3, right? v2 can be written as a linear combination of the other two, because we could solve for v2, and the same for v1. Now that doesn't always happen. That happens here because we're looking at a small set of vectors in R3. What we know what this means visually now, right? This means that all three vectors lie in a plane, right? All three vectors lie in a plane. And we could see that visually if we were to graph the three vectors, right? They're linearly dependent. We could reach any of them by using only the other two, or those three vectors only span all of our, those three vectors do not span all of R3. They only span a plane. So notice that we can relate this back to our previous work, right? That do they span all of R3? No, because there is not a pivot in every row. Are they linearly independent? No, because there is not a pivot in every column. Now, in this case, those two questions go hand in hand because it's a square matrix, right? We've got three vectors in R3. That's not the case in all situations. Okay, so we're really studying the solution to AX equals 0, right? We're really studying what we looked at back in section 1.5. Okay, let's actually make one more statement about this non-trivial solution. So each linear dependence relation we see it in one example of a linear dependence relation right there in the box. Each linear dependence relation among the columns of A corresponds to a non-trivial solution to AX equals B. To AX equals 0. We're searching for weights to put on the vectors to arrive at the 0 vector. Okay? All right, let's actually step back and look at even simpler cases, sets of 1 or 2 vectors. Okay? So let's take an example of a single vector. Okay, so suppose we have the vector v1, I'm just totally making this up, -1, 2, -5. Okay, a random vector in 3 space, or any random vector in any space. Is a set of one vector linearly independent or linearly dependent? Well, you ask yourself, what is the solution to x1 v1 equals 0? Is there any other number that I could put on x1 to achieve the 0 vector? No, the only solution that's going to work here is 0, right? So that this equation has only the trivial solution. So one vector, a set that only contains one vector is linearly independent. However, there's an exception, right? What if that one vector is the 0 vector? And then we try and ask this question, right? How many solutions are there to that equation? There's infinitely many, because if v1 is the 0 vector, then I can put any scalar in front of v1 and still arrive at the 0 vector. So this set would be linearly dependent. And this ends up being a theorem that any set that contains the 0 vector, whether it's a single vector set or a multiple vector set, any set that contains the 0 vector is linearly dependent. Let's write that down. Any set that contains the 0 vector is linearly dependent. Let's reason through that in a large set. So suppose we have a set of 4 vectors in whatever space you want, and one of them is the 0 vector. So we would try to solve x1 v1 plus x2 v2 plus x3 times the 0 vector plus x4 times v4 equals 0. Well, we automatically have a non-trivial solution because this is possible with just any made-up vector, right? Like suppose the x vector is 0, 0, 5, 0, right? That's going to work, and that's a non-trivial solution, and we can always do this if a set contains the 0 vector. All right, so let's talk about sets of 2 vectors now, instead of just sets of 1. Okay, so suppose v1 equals 3, 2, 1, and v2 equals 6, 8, -9. All right, 2 vectors in R3, right? Well, if we graph these, we would clearly see that they don't lie on the same line, right? They are not scalar multiples of each other, not scalar multiples. Okay, therefore, in space, they're going to look something like this, and this set is linearly independent. Okay, a set of 2 vectors is always going to be linearly independent unless the 2 vectors are scalar multiples of each other, or unless one vector is a scalar multiple of the other one. You might wonder, how could that be? How could one vector be a scalar multiple of the other, but not the reverse? That would be if one of them is the 0 vector. Okay, so 2 vectors are going to be linearly independent unless the vectors are scalar multiples. This set, the set that contains 1, 1, 1 and 2, 2, 2, if those are the 2 vectors, this set is linearly dependent because we can write a linear dependence relation, right? v2 equals 2 times v1, which could be written as -2 v1 plus v2 equals the 0 vector. okay? And of course, that's a non-trivial solution to AX equals 0. Okay, so the formal theorem is that a set of two vectors is linearly dependent if at least one of the vectors is a multiple of the other. The set is linearly independent if and only if neither of the vectors is a multiple of the other. Okay, the other theorems in this section I'll read, but we're not going to prove them rigorously because they're kind of intuitive. Okay, so there are three theorems at the end here, Theorem 7, Theorem 8, and Theorem 9, and we'll kind of sketch out what they say without getting too crazy about their proofs. Okay, so Theorem 7 says that a set of two or more vectors is linearly dependent if and only if at least one of the vectors in that set is a linear combination of the others. Okay, so this theorem goes both ways. So set of two or more vectors is linearly dependent if and only if at least one vector is a linear combination of the others. Notice what this theorem does not say. It doesn't say that every vector is a linear combination of the others. It just says that one of them has to be, okay? In other words, in the relation x1 v1 plus x2 v2 plus x3 v3 equals 0, one of those vectors has to be able to be solved for. One of those vectors has to have a non-zero constant in front of it. It could be that the only, it could be something like this. It could be, say, 0, 1, 0 is our only relation. I guess that would imply that that v2 might be the 0 vector. But in this case, v2 could be solved for, okay? In cases of, say, 4 vectors or larger, those are a little bit more interesting cases that we can look at in just a second. In fact, let's try one right now. Let's take a look at like a set of 4 vectors in R4. Okay, so 1, 2, 3, 4. We'll go 8, 2, or 8, 1, 3, negative 2, 4, negative 3, 2, 1. And I'm going to purposely do this, that I'm going to make the last vector a linear combination of the middle two. Okay, so I'm going to make it a simple linear combination. I'm just going to add them. 12, negative 2, 5, and negative 1. Okay, so what we see here so this is an example of 4 vectors in R4. So we see that x1 is 0, x2 is negative x4, x3 is negative x4, and x4 is free, right? So we could say that the solution to ax equals 0 is this. Well, now what does that come out to be as far as the vector equation? It would be 0 v1 plus, I should say minus v2 minus v3 plus v4 equals the 0 vector. So does it satisfy the condition of the theorem on the right side? Does at least one of the vectors, can at least one of the vectors be written as a linear combination of the others? Yes, in fact, v2, v3, and v4 can all be written as linear combinations of each other. It's v1 that's sort of, I don't want to use the word independent, but it's not part of the linear dependence relation. So you can't write v1 as a linear combination of the others. v1 sort of points off in its own direction, if you have a sense of that, right? It's like, in 4 space, we can't really visualize that, but v1 is the one that's not in the span of the other 3. Okay, Theorem 8. So Theorem 8 says if a set contains more vectors than there are entries in the vectors, then we have a linearly independent set. Okay, so if a set contains more vectors than there are entries in the vectors, then we have a linearly dependent set. So suppose you had v1 to vp, p vectors in Rn, And this is a situation where we're saying P is greater than N. So let's make a case that kind of looks like that, okay? So let's say that N is 3. So there are 3 components in each vector. And let's say that P is 4. So we're talking about 4 vectors in R3. We know that there's going to be a free variable here. In other words, there is going to be a non-trivial solution because there's no way to get a pivot in every column, right? We could go 1, 1, 1, but this guy is going to be free, right? So the existence of any free variable implies that there's a non-trivial solution to AX equals 0, which is exactly what's happening here, okay? So whenever there are more columns than rows, you have a linearly dependent set of vectors because it's guaranteed that one of those vectors is going to be able to be written as a linear combination of the others. We have a non-trivial solution by the existence of a free variable. And finally, theorem 9 is something that we've already stated. So theorem 9 just says that any set with the 0 vector is linearly independent. Sorry, said that wrong. Any set with the 0 vector is linearly dependent. So we say if a set contains the 0 vector, and this is an if and only if, right? If a set contains the 0 vector, no, it's not actually. It's not an if and only if. If a set contains the 0 vector, then linearly dependent. And we reasoned through that earlier in the lesson. Okay, there's a lot to practice here, but we'll do that. I wanted to make this kind of a concise going through the lesson. Plus, there was someone who said they were going to be absent, so this will give them an opportunity to kind of hear it the same way that you all in class did, and we'll practice problems together in class. Thanks for watching.